You know, we usually think of the smartest AI as being the most intelligent one, but what if that's not quite right? Today, we're going to dive into some fascinating new research that suggests a different trait is actually way more important for AI reasoning: prudence. Yeah, being cautious. We're about to see why being careful can be a lot more powerful than just being clever.
We've all been there, right? You give a super advanced AI some complex problem, and it just knocks it out of the park. Brilliant answer. Then you ask it something that feels pretty simple, and the answer you get back is just weirdly, fundamentally wrong. It's a real head-scratcher. So what on earth is actually going on inside that black box?
So the usual suspects are one of two things. Either the AI is missing some key information, that's a knowledge deficit, or its ability to think logically is just broken somehow, a reasoning flaw. But what if it's more complicated than that? What if we've been looking at this puzzle all wrong?
To get to the bottom of this, researchers came up with a really brilliant experiment. They took a classic idea from human psychology. You might have heard of it, System 1 and System 2 thinking. And they applied it to AI. They figured out a way to split the AI's thinking into two totally separate modes.
First up, they measured the AI's fast thinking, which is basically its gut reaction. And how they did this is super clever. They forced the model to answer with just one single character. This strips away all the hemming and hawing, all the deliberation, and it gives us a pure, clean measure of its raw stored knowledge. It's what the AI instinctively knows.
And then they let the AI really, think it over. This is the slow thinking part. Here it uses a chain of thought process to break the problem down step by step, kind of like you'd scribble down your work for a math problem. The final answer it gives here is what it comes up with after all that deliberation.
And this is where things get really interesting. The researchers found that the shift from that fast gut answer to the slow, reasoned one isn't just a simple improvement. Oh no, it's more like a battlefield. It's a constant tug of war happening inside the model between two very different forces.
So, this tug of war has two sides. On the positive side, you have what they call correction gain. That's the good stuff, right? That's when the reasoning process finds an initial mistake and fixes it. But then there's the negative side, the overthinking loss. And that's when that exact same reasoning process takes a perfectly correct answer and messes it up.
Let's give that positive force a friendlier name: reasoning intelligence. This is a number that tells us how likely it is that the AI's slow thinking will actually fix a mistake it made in its gut reaction. This is what we all think of when we say an AI is smart.
And that other force, the negative one, is just as important. Let's call that reasoning recklessness. This measures how often the AI has the right answer to begin with, but then it overthinks, second-guesses itself, and talks itself into a mistake. It's basically a measure of AI self-sabotage.
Okay, so now we have these two new tools in our belt: intelligence and recklessness. And by separating them, researchers could finally compare different sizes of AI models in a totally new way. And what they found, well, it's pretty surprising, and it's really the core idea of this whole explainer.
So let's see how this works. Here we have a smaller model, an 8 billion parameter one. Its raw knowledge, or fast-thinking accuracy, is around 60%. Not bad. Its reasoning intelligence is pretty decent too. It can fix 40% of its initial mistakes. But whoa, look at that recklessness rate. 17%. That is high. It's constantly tripping over its own feet, turning right answers into wrong ones.
Now let's bring in the big guns, a much larger 70 billion parameter model. Its raw knowledge is way better, up at 81%, just like we'd expect. But check this out. Its reasoning intelligence is actually a little bit lower than the small models. The real story, the huge difference, is its recklessness. It just plummets, all the way down to 7%. The big model isn't necessarily more intelligent in its step-by-step reasoning. It's just vastly more prudent. It's more careful. And this prudence leads to a totally stunning paradox. If you actually calculate the net gain from reasoning, so you take the number of corrections and subtract the number of overthinking screw-ups, the smaller 8B model gets a net gain of almost 6 correct answers for every 100 questions. And the smarter 70B model, it only gains about 1.5.
Wait a second. How is that even possible? This feels completely backwards.
right? How can the bigger, more powerful model actually gain less from its own reasoning? Well, the answer is actually really profound. It's because the large model's initial knowledge is just so much better to begin with. Think about it. Its fast thinking has already aced most of the easy and medium difficulty questions, so that leaves its slow thinking to wrestle with only the absolute hardest problems, where making corrections is way tougher and the net gain is just naturally going to be small.
Okay, so this whole split between fast knowledge and slow reasoning, it's not just some abstract theory. The researchers were actually able to find where these different processes are happening inside the AI's brain, its neural network. So when they looked inside the transformer architecture, they found that the lower layers are basically the file room. They handle retrieving basic knowledge, and their activity looks almost identical for both fast and slow thinking. But it's in the higher, more abstract layers where the paths split. That's where the complex work of reasoning and making adjustments really kicks into gear. And this chart just shows it so perfectly. It uses a metric called CKA, which is basically a way to see if two parts of the network are thinking about a problem in the same way. And look, it's plain as day. In the lower layers, on the left, the similarity is super high. They're doing the same job. But then, in the higher layers, that similarity just falls off a cliff. That is the spot in the network where deliberate reasoning takes over and forges its own path.
So why does any of this matter? What's the big takeaway here? Well, it matters because this whole framework isn't just some cool academic paper. It actually gives us a powerful new diagnostic toolkit to fix AI failures with, like, surgical precision. So now, instead of just guessing, we can diagnose the real problem. If a model has low fast-thinking accuracy, we know it's a knowledge deficit. The AI just doesn't know the facts. The fix? Add more information, maybe with a technique like RAG that lets it look things up. But if the knowledge is good and the recklessness rate is high, that's a reasoning deficit. The AI has bad thinking habits, and the fix there is totally different. You need to use targeted training or fine-tuning to teach it to be more careful, more prudent.
This all leaves us with one last, really provocative thought to chew on. For years, we've all just assumed that scaling up AI, building bigger and bigger models, is all about a race to create more raw intelligence. But what if this research is telling us something else? Perhaps the main benefit of making these models bigger isn't just making them smarter, but making them more cognitively stable, more prudent, and less likely to be derailed by their own thoughts. What if the real future of AI isn't just about intelligence, but about wisdom?